Jai Hind everyone, I am Dr. Nitisha Shrivastava, Assistant Professor in the Department of Electrical and Electronics Engineering in Akgec Engineering College in Ghaziabad in Uttar Pradesh in India. In this lecture, we will look at how do we assess the stability of a given transfer function using the Bode plot sketch. So when we sketch the Bode plot, we have certain procedure to follow. There are two ways which you can do that. One procedure is this. We can express the transfer function in the standard form, then identify the pole zero frequencies. Then we express the magnitude and phase responses, and then we sketch each magnitude and phase response on the semi-log graph paper, and each term of that magnitude and the phase response is added to get the total response of the system. Other way is we first identify the lowest frequency on the given transfer function, and then the logic of using the increase in the slope for a zero and decrease in the slope for a pole. As we identify this, then we move along the frequency axis with increase or decrease in the slope at the each corner frequency associated with a pole, or with a zero, or with a complex pole, or with a complex zero. This procedure is repeated for both magnitude and phase till all the frequencies, corner frequencies are covered. Now, how do we assess the stability of a system using the Bode plot? So, this sketch gives us the stable system, and this sketch lets us know that if this is the response, then the system will be unstable. This is drawn on a semi-log paper, and y-axis is the magnitude here. Here y-axis is the phase, and the x-axis in both the cases is the log scale of frequency omega. This is omega, this is also omega, this is the magnitude, and this is the phase. Now, this is plotted one below the other, like this is the magnitude plot and this is the phase plot, just because now when we draw the Bode plot, we come across the different slopes, and when the final total response is taken into consideration, if the Bode plot is crossing the 0 dB line, the frequency at which the Bode plot crosses the Bode magnitude plot crosses the 0 dB line is termed as the gain crossover frequency, represented as omega GC. And similarly, when we plot the phase on a semi-log graph paper, this point, this frequency where the phase plot crosses the minus 180 degree mark, this is known as the phase crossover frequency, which is known as omega PC. The frequency at which the phase angle is equal to minus 180 degree is known as the phase crossover frequency, and the frequency at which the magnitude is 0 dB, its frequency is known as the gain crossover frequency. Now, once these two frequencies are identified, in the Bode plot sketch, we mark a line from this gain crossover frequency and come till the phase plot, this point. Now, this is the same frequency, the gain crossover frequency. this distance of the phase value, from minus 180 till this point is known as the phase margin. And if this is lying above this minus 180 degree, then this is termed as a positive phase margin. And this point at the phase crossover frequency, we draw a line starting from here till this. So, this distance is known as the gain margin in decibels, whereas the phase margin is in degrees and gain margin is in decibels. This distance is known as the gain margin, and this, if this is lying below this line, then this is known as the positive gain margin, and this is known as the positive phase margin. For a system to be stable, it is necessary that the phase margin be positive and the gain margin be positive. Now, if we find that this magnitude Bode plot has a gain crossover frequency, that means the magnitude of the transfer function when it is 0, what is the frequency at that point? So, that is known as the gain crossover frequency. So, in this plot, when the plot crosses this 0 dB line, this is my 0 dB line and this is the plot. When this plot crosses the 0 dB line, this is known as omega GC, and you mark this down. This distance is known as the phase margin, and the value below this minus 180 degree is a negative value. So, this negative value is termed as the negative phase margin, and for such kind of response, the system is unstable. If the system is having a negative gain margin and a negative phase margin, then the system is unstable. So, it clearly means that for the system to be stable, both the gain margin and the phase margin should be positive. So, this distance below the 0 dB line and here the distance above the minus 180 degree. Here you can see that this is above the 0 dB line. So, it is a negative gain margin and this is below the minus 180 degree mark. So, this is a negative phase margin for an unstable system. So, this is how, looking at the sketch of the Bode, we can assess the stability of the system. And also, if it is required that the system be stable, that means you need to shift the plot up or down. So, shifting the plot up or down requires the change in the value of the magnitude, that is change in the value of the gain. Okay, so, we will take up one example and understand that. So, Bode plot is sketched on a semi-log graph paper. This is termed as the decade, as we are talking about the slope, that is plus or minus 20 dB per decade or plus or minus 40 dB per decade. So, in a semi-log graph paper, this is a decade. Also, just not between 1 to 10 is a decade. You can also mark, for example, from 3 to 30. This also will be termed as decade, or if you are marking it from, for example, 9 till 90, this will also be termed as a decade. So, when we sketch it is on the Bode plot, we can consider if our corner frequencies lies at a point which is not 10, 1 or 100 or 10 to the power 3 or 10 to the power 4 or 0.1 or 0.01, we can mark that decade as the distance from 9 to 90, 8 to 80 or so on from 0.8 to 8 or so on. So this is the semi-log graph paper. Frequency is on the x-axis, which is a log scale, whereas magnitude and phase are on the y-axis, which is a linear scale. So this is the table to be referred to sketch a Bode plot. These are the factors, and this is the slope for magnitude, and this is the slope for the phase. The table continued for different factors, a constant value, 0 at the origin, pole at the origin, a simple 0, this is a simple pole, and this is the complex 0, and this is a complex pole. So, to draw a Bode plot, this table needs to be referred. We can take one example to understand. So, what does this example reads? This example reads that we need to construct a Bode plot for a unity feedback system having Gs equal to 10 into s plus 10 divided by s into s plus 2 into s plus 5. From the plot, obtain the gain margin and phase margin. Also, comment on the stability of the system. So, as it is known that to sketch the Bode plot, we have to bring it into the standard form, that is 1 plus st. To bring into 1 plus st form, in this case it is s plus 10. So, I have taken 10 outside here, and s plus 10 here, 10 outside here. So, if 10 goes outside, this becomes s by 10 plus 1, and on the denominator there is a s. I take 2 outside here. So, this becomes s by 2 plus 1, and I take a 5 outside here. So, this becomes s by 5 plus 1. So, 5 into 2 is 10. Right, 5 into 2 is 10 here, and so this becomes now 10, and this is, right, we already have a 10 constant here. This constant 10 is there, and this 10 and this factors which we have taken out to bring it into the standard form gets cancelled out. So, this 10 is as it is. And 1 plus 0.1 s, 1 plus 0.5 s, and 1 plus 0.2 s. So, bringing it into the standard form, that is the basic requirement to sketch a Bode plot. Then put s is equal to j omega. So, when we put s is equal to j omega, we get the expression 10 into 1 plus j 0.1 omega. In place of s, we have just put j omega. So, in place of s, it is j omega, 1 plus j 0.5 omega, 1 plus j 0.2 omega. So, to sketch the Bode plot, we need to have the magnitude and the phase equations. So, what is the magnitude and the phase equations? In this case, it will be, this will be 20 log 10, this will be 20 log 0.1 omega plus, and here it will be minus 20 log for this case. It will be in the numerator, minus sign for this also and for this also. Now, instead of going that way, we can first identify the various factors. So, what are the factors in this? We have a constant 10 in the expression, that is 10 into 1 plus 0.1 s, 1 plus 0.5 s, and 1 plus 0.2 s as the pole. So, we will understand what are the corner frequencies. The lowest frequency is arranged first. So, the lowest frequency is 2, and here next is 5 and next is 10. So, corresponding to that, what are the factors? In this case, we have a constant, we have a pole at the origin, and this is corresponding to a simple pole. This is corresponding to a simple pole, this is corresponding to a simple 0. So, what will be the asymptotic log magnitude characteristics? it will be a straight line of 0 dB starting from 20 log 10, since this factor is 10, and for this we will be having a pole, because it's a pole. The slope is minus 20 dB per decade and its value is 0 dB at omega equal to 1. That means it is passing through omega equal to 1, and this will be a straight line of minus 20 dB per decade originating through omega equal to 2. And this is a straight line of minus 20 dB per decade originating at omega equal to 5. These are nothing but the corner frequencies. Till then its value will be 0, and in this case it will be plus 20 dB per decade originating at omega equal to 10, which is the corner frequencies. Regarding the phase expression can be written as, for the constant factor it is 0 degree. This is for the simple 0. This is the pole at origin. These minus sign here indicate that the term has come from the denominator to the numerator. Therefore, this angle is being subtracted. Whereas in these two cases, you can see that there is an addition of the angle. In this expression, if I place the values of these omega, that is the frequencies 0, 0.1, 0.5, 1, 2 and so on, then correspondingly what will be the phase. So, this table is constructed by keeping the value of omega as mentioned here, minus 90, minus 93 and so on we get. So, we can draw the phase plot directly putting these values, and we can see that there is a transition here starting from minus 90. We need to at least look for values crossing minus 180 degree. So, we can see here that the table which we have formed crossed minus 180 degree, because when the phase plot crosses the minus 180 degree line, we get the phase crossover frequency. So, you can take more values or you can stop, because once we have been assessing the stability and we got this minus 180 degree mark, then the values chosen can be simply to sketch the plot. So, how do we sketch the plot? This is simple. What I have shown here is the Bode plot taken from the MATLAB. Now, to sketch the plot, the constant term what I have taken here, we can show here also. The constant value what we are getting it as is 10. So, I can mark here 10. This is the term 10 and it is a first order system. It is a type 1 system. So, I will mark here 10 in this point. I will mark here 10. And then since it is a pole at the origin, it is a type 1 system because we have one pole at the origin. So, that means one pole of at the origin is minus 20 dB per decade. So, this is my decade line, minus 20 dB per decade. So, here I have as here I can mark it as 10. This is the point where I am marking it as 10. And minus 20 dB per decade means this is the line. This is 1 decade from here, and this is and this is 20 dB. So, this will be my line. This will be my line, and the slope can be extended till the initial frequency whatever I have taken. This is the first line I will mark here. I have first placed the 10 here, and then I have taken this as minus 20 dB per decade, and this can continue. Now, the first corner frequency what I have obtained is 2. I have taken care of these two things by marking 10 and this minus 20 dB per decade slope. My first corner frequency is at 2. So, the first corner frequency is at 2. This is the 2. The slope will change at 2. This is the mark 2. The slope will change at 2. This is the point at 2. So this will be 2. This is 10 raised to 0, 1 and 2. The slope will change at the 2 line. So this what I had drawn is at 10. The slope will change at 2. The slope will change at 2. We can change the color of the pen for that. The slope will change at 2, and how much? Since it's a pole, so minus 20 dB per decade. So this will be minus 20 dB per decade till what line? Till the next corner frequency. Till the next corner frequency means till 5. So till 5, this is 1, 2, 3, 4, 5. Till 5 we will be having this value, this till 5 this line continues. Then at 5 we have another corner frequency which is a pole. So here again the slope changes, it's a pole, so minus 20 dB per decade again. So this will be minus 40 dB per decade, and then again which is the next corner frequency is 10, so which is a 0. So in 0 it is that we have plus 20 dB per decade. So again at 10 the corner frequency, the slope will change. The slope will change at 10 again, that is at this point, So these are the 4 different lines obtained, and the point where this slope cuts the 0 dB is the phase gain crossover frequency, and corresponding to that we get the phase crossover frequency. And phase plot can be drawn with these values, keeping in mind this table, we can draw the phase plot. So this system, these values of gain margin and phase margin, gain crossover frequency and phase crossover frequency has been obtained from MATLAB. It can also be cross-checked with this plot. So this is the plot what I am telling about is, this is the minus 20 dB, this goes up till the 10 line, but it is changing here. It has to be marked like this, but it is changing at 2, then at 2 it continues till 5, at 5 again it is changing, and that is minus again minus 20 added on, at 10 again it is changing. So this distance is called as the gain margin, and because from here this is the point where the phase plot is crossing the minus 180 degree mark. So this distance from here is the phase margin, and phase margin is coming out to be positive, and here we can refer to the actual values mentioned here of the phase margin and the gain margin irrespective of what is mentioned here. This is the correct values of phase margin and the gain margin. This is the gain margin and this is the phase margin, gain crossover frequency and the phase crossover frequency. When referred to this point is the phase crossover frequency. Corresponding to that we have the gain margin, and this is the gain crossover frequency, and corresponding to that we have the phase margin. So this is how we can sketch the Bode plot. Similarly, I have a second example here. In this we need to determine the system gain K for the gain crossover frequency to be 5 radians per second. So this is already in the standard form. We have 2 zeros at the origin. So for this factor S square, since it is 2, it will be plus 40 dB per decade, which is passing through omega equal to 1. This will be the pole, so minus 20 dB per decade. This is again a pole, minus 20 dB per decade. These are the corner frequencies 5 and 50. Now in this plot we can see that this is the plus 40 dB per decade line due to the factor 1 upon 1 S square. right? We have, yes, plus 40 dB is not 1. We have it for the factor s square, which is crossing through this 1, and then this is the resultant plot. Now, this distance is coming out to be 28 dB. The question is that we have to determine the system gain k for the gain crossover frequency to be 5 radians per second. So, looking at the graph, it can be understood this distance at 5 radians per second. So, this distance is 28 dB. Therefore, if the gain crossover frequency is required to be 5 radians per second, then the magnitude plot must cross the 0 dB line at 5 radians per second. So, for this the plot has to be brought down by 28 dB. So, this plot, if now the phase is crossing at 1, but if it has to cross at 5, that means the entire plot has to be brought down. So, this point becomes here. So, this distance, that means it has to come down at least by 28 dB. And hence, what would be the value of k? The value of k would be 20 log k is minus 28. Therefore, k will be 0.04. So, thus we can, looking at the sketch, we can change the value of gain to particular gain frequencies, gain crossover frequency, phase crossover frequency, or to adjust the gain margin and the phase margin. Thank you.